Welcome to this lesson about data cleaning and data quality with SQL. In real projects, data is not always perfect. Sometimes records are duplicated. Sometimes important values are missing. Sometimes a fact table contains keys that do not exist in the dimension table. And sometimes the data is simply old, incomplete, or inconsistent. The goal of data quality is simple. Detect bad data before it reaches reports. Think about a banking dashboard. If the dashboard shows the wrong balance, the wrong number of transactions, or missing customer information, the issue is not only technical. It can affect business decisions, compliance, audit reviews, and production support. That is why SQL validation queries are so important for data engineers, data analysts, and analytics engineers. In this lesson, we will walk through 7 practical checks: duplicate detection, null validation, referential integrity checks, outlier checks, reconciliation queries, source versus target comparison, and data freshness checks. The full pipeline is shown at the bottom of the slide. Data comes from source systems, lands in staging, goes through SQL quality checks, and only then becomes trusted reports. A good data engineer does not only move data. A good data engineer protects the quality of the data before people use it to make decisions. Now, let us start with one of the most common data quality problems: duplicate detection. A duplicate happens when the same business key appears more than once in a table. For example, the same customer ID may be loaded twice into the customer table because of a repeated file load, a bad merge process, or an incorrect integration from a source system. At first, a duplicate may look like a small technical issue, but in reporting, it can create serious business problems. Duplicates can inflate customer counts, double count sales, generate repeated statements, trigger duplicated alerts, and make dashboards look more successful or more problematic than they really are. In the center of the slide, we can see a simple customer table. Customer ID 101 appears twice for Anna, and customer ID 103 appears twice for Sarah. These are duplicate business keys, and they should be reviewed before this data reaches the final reporting layer. The SQL query on the right shows a classic validation pattern. First, we select the customer ID. Then, we count how many records exist for each customer. After that, we group the data by customer ID. Finally, we use the halving clause to keep only the groups where the count is greater than 1. The key idea is simple. Group by organizes records by business key, and halving filters the groups that appear more than once. This query returns only the customer IDs that have duplicates, making it easy to investigate and clean the data. A common interview challenge is to detect duplicates using more than one column. For example, maybe the customer ID is not reliable, but the combination of email and phone should be unique. In that case, we group by email and phone, and then apply the same condition: having count star greater than 1. This is one of the simplest, most practical, and most powerful data quality checks in SQL. It helps protect reports from inflated numbers and gives the data team an early warning before bad data reaches business users. The next check is null validation, one of the most important controls in any data pipeline. A null means that a value is missing, unknown, or was not provided by the source system. Not every null is a problem. Some fields can be optional, but when a null appears in a critical column, it can break joins, damage calculations, and create incomplete reports. For example, if customer ID is null, we may not be able to connect a payment to the customer dimension. If amount is null, totals, balances, and financial reports can become inaccurate. If transaction date is null, the record may be excluded from the correct daily, monthly, or yearly reporting period. In the center table, we can see 3 clear data quality issues. One row has a missing customer ID, another row has a missing amount, and another row has a missing transaction date. These records should be detected before they move into the final reporting layer. The validation query is simple, but very powerful. We select all records from the staging payments table where customer ID is null, or amount is null, or transaction date is null. This query acts like a safety filter. It catches incomplete rows early before they affect dashboards, reconciliations, financial reports, or downstream business logic. A strong best practice is to validate mandatory columns as early as possible, usually in the staging layer or right before loading the final table. The earlier we catch the issue, the easier and cheaper it is to fix. The challenge example at the bottom shows a monitoring query. Instead of returning every bad row, it counts how many null values exist in each important column. This is very useful for data quality dashboards, automated alerts, daily production checks, and SLA monitoring. The key lesson is this: critical columns should be validated on every load. One missing value may look small, but it can create many downstream problems if it is not detected on time. Now let us talk about referential integrity, a key concept for building trustworthy data models. Referential integrity means that records in one table should correctly connect to records in another related table. In simple words, if a table contains a key, that key should exist in the table it references. A very common example is the relationship between a fact table and a dimension table. For example, a fact sales table may contain a customer key, and that key should exist in the dim customer table. In the center example, the fact sales table contains customer key 999. However, the dim customer table only contains customer keys 101, 102, and 103. That means customer key 999 has no match in the customer dimension. This type of record is called an orphan row. An orphan row is dangerous because the transaction exists, but the descriptive customer information does not. In a star schema, this can create missing customer names, incomplete dashboards, incorrect aggregations, and broken business analysis. The SQL query uses a classic validation pattern, a left join from the fact table to the dimension table. The left join keeps all records from the fact table. Then we filter the result where the dimension key is null. In plain English, this query says, show me all fact records that could not find a matching dimension record. The result is a list of orphan fact rows that should be reviewed before the data reaches the reporting layer. The challenge version counts how many unmatched rows exist. This is very useful in production support because sometimes you do not need to inspect every bad record immediately. First, you need to know whether the issue exists, how large it is, and whether it breaks your data quality threshold. This type of check is extremely important in banking, compliance, audit traceability, and reporting systems. It helps confirm that every transaction can be connected to the correct business context before users make decisions with the data. Next, we have outlier checks, a very important technique for detecting suspicious or unusual values in your data. An outlier is a value that is much higher, much lower, or very different compared with the normal pattern of the dataset. But here is the important part. Outliers are not always errors. Sometimes they represent real business events, like a very large payment, a special corporate transaction, or an unusual customer behavior. However, they still need to be reviewed because they can also indicate bad data, fraud, incorrect transformations, duplicate loads, decimal point mistakes, or unexpected source system behavior. In the visual example, most transaction amounts are small and stay close to the normal range. But one transaction is extremely high, close to 9,800. That value immediately stands out from the rest of the data, which makes it a strong candidate for investigation. A simple and practical validation query uses business thresholds. For example, we can select transactions where the amount is less than 0 or greater than 10,000. This type of rule is easy to understand because it comes directly from business logic. A negative payment amount may not be allowed. A very large transaction may be valid, but it may require approval, investigation, or additional validation. At the bottom of the slide, we also see a more advanced anomaly check. This query compares each transaction amount against the average plus 3 times the standard deviation. That is a statistical way to detect values that are far away from the normal behavior of the data. For interviews in real projects, remember this key idea. Outlier checks should combine SQL logic with business context. SQL helps us find suspicious candidates, but the business rules help us decide whether those values are truly wrong, valid exceptions, or transactions that simply need review. Now, let us move to reconciliation queries, one of the most important controls for validating data across a pipeline. Reconciliation means confirming that record counts, financial totals, and key metrics match between data layers. In simple words, we want to make sure the data that entered the pipeline is the same data that arrived at the next stage, without unexpected losses, duplicates, or changes. For example, If the source system contains 10,000 payments, then the staging table should also contain 10,000 payments after ingestion. If the source total amount is 4,500,000, the staging total should match that number as well. In the center example, source payments and staging payments match perfectly. They have the same record count and the same total amount. That is a good sign because it tells us the ingestion step worked correctly. But the final payments table shows only 9,998 records and a smaller total amount. That is a mismatch. This mismatch tells us that something changed between staging and final. Maybe 2 rows were filtered out by mistake. Maybe a transformation failed. Maybe a join removed records. Or maybe the data was only partially loaded. The SQL query on the right uses union all to compare 2 layers in one result set. The first select returns the source layer, the record count, and the total amount. The second select returns the staging layer, the record count, and the total amount. This format is simple, clean, and powerful because it allows you to compare multiple layers side by side in a single output. Good reconciliation checks usually include record counts, sum of amounts, and distinct business keys. These 3 checks help confirm that the volume, the financial totals, and the unique business entities are consistent across the pipeline. This is especially important in banking, monthly close processes, compliance reporting, production support, and any system where totals must be reliable. The main idea is this: before trusting the report, confirm that the numbers survive the journey across the pipeline. Data should not only move from source to target, it should arrive complete, accurate, and consistent. The next topic is source versus target comparison, a powerful validation technique for checking whether 2 tables contain the same expected data after a transformation, load, migration, or production release. In simple terms, this check answers an important question. Did the data arrive in the target table exactly as expected? In the center of the slide, we compare staging customers against final customers. The staging table contains customer 104, David, from Austin, with status inactive. But this row is missing in the final table. That's a missing row issue. We also see that customer 103 exists in both tables, but one value changed. In staging, the city is Chicago. In final, the city is Boston. That is a changed value issue. So this comparison helps us detect 2 common problems: records that disappeared and records that changed unexpectedly. The SQL pattern on the right uses except. The first query returns records that exist in staging but do not exist in final. This helps us find rows that were expected in the target table but never arrived. The second query does the opposite. It returns records that exist in final but do not exist in staging. This helps us find extra rows that should not be in the target table. Using both directions is important because source versus target comparison is not complete with only one query. One direction finds missing target rows, and the other direction finds unexpected extra target rows. In some SQL systems, especially Oracle-style SQL, the equivalent operator may be minus instead of except. The idea is the same: compare 2 result sets and return the differences. The challenge example compares only by customer ID. This is useful when you want to confirm that the same business keys exist in both tables without comparing every column. This type of validation is extremely useful before production releases, after ETL or ELT changes, during migrations, or when debugging why a dashboard changed unexpectedly. The key idea is this: source versus target comparison helps prove that your transformation produced the expected result, not just a result that looks correct at first glance. Finally, we have data freshness checks, a critical validation step for making sure your data is not only correct, but also up to date. Data freshness means checking whether a table was updated within the expected time window. A table can have the right structure, valid keys, no duplicates, and no nulls, but it can still be wrong if the data is stale. In other words, the data may look clean, but if it is outdated, the report can still mislead the business. For example, imagine a daily banking report that is expected to use today's transactions and balances. If the table was last loaded yesterday, the report may show outdated balances, missing transactions, or incomplete customer activity. In the center dashboard, transactions and customers are marked as fresh because they were loaded recently, but balances are marked as stale because the latest load is older than the expected refresh window. The first SQL query checks the latest load timestamp using max load timestamp. This tells us the most recent time the table was updated. The second SQL query goes one step further and creates a simple freshness status. If the maximum load timestamp is within the expected window, the table is marked as fresh. Otherwise, it is marked as stale. In real projects, every critical table should have a defined refresh expectation. For example, transactions may need to be loaded every morning by 6 a.m. Balances may need to be ready before the business report opens. Customer data may need to be refreshed before downstream jobs start. A strong production process should monitor the last load time, define clear refresh windows, and trigger alerts when important tables are late. The final takeaway is simple. Trusted data starts with good validation. Before publishing reports, validate duplicates, nulls, keys, totals, source versus target differences, outliers, and freshness. That is how SQL becomes more than just a query language. It becomes a quality control tool for reliable data engineering, helping teams protect reports, reduce production issues, and build trust in the data.